Okay, hello everyone. Okay, so today we're going to learn about something new in a direct current. Topics we call as Wheatstone bridge. Okay, the first thing why it's called as Wheatstone bridge is actually it looks like a bridge. Okay, there were like four resistors were arranged. It looks normally like a analogous to a bridge. Okay, so Wheatstone bridge is used to measure unknown resistance of the resistor. Okay, let's say we have three resistors and one unknown resistor. We can use it to find how much the resistance of the one of the resistor. So let's say we have here, this is the common diagram of Wheatstone bridge. We have four resistors R1, R2, R3 and Rx. Okay, and then we have one EMF and a coupled meter between uh, C and D. Okay, so this is a very simple Wheatstone bridge. There will be a junction between the A over here and to over here, up and down to the C and to the D, and from C to D it will be coming back junction, going back into the B, and then it goes back to one single loop. Okay, so the current goes to the A and current goes back from B to the EMF. Okay, so you can see the current, how it goes, where the junction goes. Okay, and one more important thing in Wheatstone bridge, the uh, the meter of the 2 points between C and D will show 0. It means that the potential difference between C and D is 0. So there are no current pass through and there are a 0 deflection on the galvanometer. Okay, so Wheatstone bridge is said to be balanced when no current flows through the galvanometer. Okay, so potential difference C and D is equal. So same diagram as before. Hence, IAC equals to ICB or equals to I1, and IAD equals to IDB equals to I2. Okay. Why you remember I1, I2? Because it's separated from the main current over here. So it was separated I1 and I2 and it combined back at the B point over here. So then potential at C equals to potential at D. Therefore, VAC equals to VAD. So VAC, this, okay, V, potential difference, is equals to VAD over here. So both of them are equal. Okay. And VBC, BC is over here. V, potential difference. And VDB is this one. Okay, where potential difference is equals. So up and down are equals. You can say upper resistor and lower resistor are equals. So since V equals IR, Ohm's law, thus I1 R1 equals to I2 R3. Okay, I1 R1, you can check I1 R1 equals to I2 R3, and I1 R2 equals to I2 RX. Rx means that the resistance that we want to measure. Okay, dividing give I1 R1 divided by I1 R2 equals to I2 R3 equals to I2 Rx. So Rx you can find the how much is the resistance of Rx by equals to R2 divided by R1. So R2, I'm using another color, R2 divided by R1. So going to the left, R2 divided by R1 times with R3. Okay, so you can see the pattern. This resistor, okay, divide by this resistor, okay, divide and times with this resistor. So divide and times. Okay, and gamma meter must be in between like this. Okay, you can see the pattern. In visually type pattern, you can see that the G like this. So it cross, divide, and times with the below. Okay. So this is a meter bridge. Okay, a little bit modification of a Wheatstone bridge. We call it as meter bridge. Okay. So meter base does not have any it's not it's it has only two resistor, and they are the two resistor bottom resistor was replaced by a single uniform wire. So you can see over here there is one resistor over here, one more resistant, and then this is a long wire, one usually 1 meter, not very long. So there will be resistance on L1. You know that when you have a longer length of wire, there will be higher resist. The longer the resistance or the higher the resistance, so we can put a jockey over here, so we can slide left and right. So there will be R A, R B, R C, and R D. So there are four resistors, same as the one you see before, and the gamma meter in between. Okay. Uh, So this is the meter bridge circuit. Okay, so the meter bridge is balanced when the jockey J is such as position of dark wire AB that there is no current through the galvanometer. Thus, the current I flow through the resistance Rx and R, but the current I2 flows in the wire AB. So you can see they are same as before. One I goes up, one I goes down. Okay. So let Vx potential across Rx, and V is a potential flux across R. Okay. So valence coefficient Vx equals to Vaj and V equals to Vjb. By applying Ohm's law, thus IRx equals I2 Raj and IR equals to I2 Rjb. Okay, dividing this, you can get where Raj equals to rho L over A, resistivity. Okay. RJB equals to rho L over A, and you have Rx is to L1 over L2 times if you R. Okay, so L1 over L2 times with the R, L1 L1 over L2 times with the R. You can see the geometry is still there. Okay, so you can see it is divide and then times, then you can find the Rx. Okay. Okay, an unknown length of platinum wire, 0.920 in diameter is placed as the unknown resistance in Wheatstone bridge, as shown in figure. Okay, so you have here 1, 2, 3, 4, and then this is showing that this is a what you call this resistor where you can change the resistor, what we call is a rheostat. Okay, we can change the resistance to be higher or lower. Okay, so resistor R1 and R2 are resistance 38.0 ohm and 46.0 ohm, and balance is achieved when switch is closed. Okay, switch is closed over here, and R3 is 3.48 ohm. Okay, calculate the length of platinum wire if resistivity is 10.6 times 10 power negative 8 ohm per meter. So it says that so this is a wire over here. Rx is a wire. Actually, it's not a resistor, it's a wire, very long wire, and it goes back over here. And the resistivity is 10.6 times 10 power negative 8 ohm per meter. Okay. So what is the length of the wire? And we know that the longer the length, there will be the higher the resistance. Okay, so this is unit for resistivity. It's not the unit for the resistance. So solution is diameter given, R1 given, R2 given, R3 given, and rho equals to 10 also given. At the balance condition, the ammeter reading is 0. Thus, the resistance of the platinum wire is given by Rx over R3 equals to R2 over R1. Okay. So Rx is 4.21 ohm. Okay, this is resistance of the Rx. From the definition of resistivity, thus rho equals Rx over L. Okay, if you can remember, Rx equals to rho L over A. Okay, now we're going to use resistivity as the equation title, and A equals to pi d square over 4, and you have here L equals to 26.4 meter. It's very long wire there, 26 meter, 0.4 meter. Okay. Number 2, exercise number 2. In figure, we have PQ is a uniform wire of length 10 meter and resistance of 10 ohm. E1 is an accumulator of EMF 2 volt and negligible internal resistance. R1 is a 15 ohm resistor and R2 is a 5 ohm resistor when the S1, S2 open. Gamma meter G is balanced when QT is 62.5 cm. When both S1 and S2 are closed, the balance length is 10 cm. Calculate A, the EMF of the cell, B, the internal resistance of the cell, C, the balance length of a QT when S2 is open, S1 is closed, the balance times Q when S1 is open and S2 is closed. Okay. So this is actually is not a question on Wheatstone, but this is just a revision on the potential divider. Okay. So this is another question you can use. You can try it out. Okay, the answer is 7.50 ohm. Okay, and we have a potential meter with length of 100 centimeter and resistance of 5 ohm connected to driver cell of EMF 2 volts and enable internal resistance. Calculate the length of potentiometer. So this is a question of potentiometer also, and you have it. Okay, so I'm going to give out some of the question you can do by yourself after this, and then we're going to discuss about the answer. Okay, see you next time. Bye bye.